started. So as I promised to you, we have some tentative plans for the final exam, which will happen next Monday. So I'll just go over them with you, right? So first of all, what to expect for our final exam, right? What's the coverage? So stated in our course syllabus, your final will be cumulative, or I say comprehensive, right? So the idea is the final covers everything we discussed this quarter. So that means midterm 1 material, midterm 2 material, plus all of chapter 5 and chapter 6. I originally planned to cover a little bit of chapter 7, which is the phase rule, but I don't think I will be able to finish that without rushing our chapter 6. So let's just end at chapter 6. So I'll spend today and Wednesday to go over all of chapter 6. My lecture note for chapter 7, which is the phase rule, is available on Bruinlearn. So if you wish to use it as an extra reading or reference for your future, that's fine. It's open there, right? It's already uploaded there. But we only test you on everything along until like chapter 6, which is this Wednesday. And then when and where, so you are my lecture 2. So your exam will take place next Monday, 8 a.m. to 11 a.m. I know it's 8 a.m. I don't make that decision. I can't change anything. I'm sorry, but that's when it's going to happen. And your final exam will be at Boiter Hall, 3400. Again, your final exam time and place are decided by the registration office. I have absolutely no control. I'll be there with you, but I can't change anything for your final exam. What to expect for the final exam? Like your midterm exam, your final exam will be open book, open note. You should already know what to expect. Anything on paper is fine, textbook is fine, nothing electronic. And the structure of your final exam that's a little bit small to see, but you can see it on your phone. It's basically the same style as your midterm exam, but it's double the length since your final exam is 3 hours, right? So specifically, we're expecting 20 true and false problems, and then 10 short answer problems, and then 2 comprehensive problems. So it's double the length of our midterm exams, but you got triple the time. So hopefully you have a little bit more time to think about the problems. And also, I still have 10 extra credits left for the class. We should have a total of 30 extra credits. I already used it in some of the surveys so far. I still have 10 left if I do the calculation right. But nevertheless, whatever left over of the extra credit will be added onto the final exam. I'll have a quick extra credit type of questions for you to answer. What to expect after the final exam? Well, your TA and I are very fast graders, so I'll try to grade your final exam as soon as possible. We'll grade your final exam on paper, so that means you won't be able to see a scan of your final exam. This also avoids problem of like Gradescope didn't read it very well, etc. But you only see a grade posted on your Bruinlearn website once we finish grading. We do not take regrade request for the final exam. If you want to see your physical copy of the final exam, we offer that. I'll post it after we finish grading. But basically, the whole point is we don't have regrade requests for the final exam. What's next? Okay, discussion worksheet. So this week, you have one last discussion worksheet focusing on chapter 6. So that's discussion worksheet number 8. Now, I want to note it because your discussion worksheet notes, discussion worksheet 8 will be due a little bit early, which is this Friday. So the whole reason here is I asked your TA to make your worksheet 8 a little bit shorter, means you have less questions graded based on accuracy, but we want it to be due by Friday so we can post the answer key. And you'll be able to use the worksheet number 8 and also the answer key to study for the final exam. All right, so that's a whole point of worksheet 8. And I just want to remind everyone it's going to be due a little bit early, so you know what to expect, right? So don't wait until like Friday and realize you don't have enough time to work on it. What else? Study suggestions. So the 3 study suggestions are pretty much stays the same. You should already know what to expect, right? Study, use your discussion worksheet, use your chapter end problems, make your own formula sheet, and also write down your equation, what's in your mind when you're setting up the problem. We give partial credit. I also added one last paragraph here. It's like practice your final exam with a timer on. It doesn't mean like you need to have a full final exam and you time yourself. It's more like, hey, how much time do I need to answer a true and false problem? Right? If I need like 2 minutes per problem, so you know how to partition your exam time accordingly. So that's what I mean by having a timer on. And at the very end, the UCLA course evaluation is on, so please log into my UCLA website and finish your course evaluation. We won't be able to see your evaluation until we submit your final grade, so it's safe. Just say anything you like. We won't make the final exam super hard because, I mean, I don't know, right? But nevertheless, so it's open, and please finish that course evaluation, and then click that link to say like yes for that question to get like 4 extra credit. If you say no, you also get that 4 extra credit. It just makes us very confused. But nevertheless, that's all my other announcement for the final exam. Let's see if we have any questions. These are the tentative plans. I'll have likely I won't change it. If I change anything, I'll let you know on Friday. Nope. Okay, sounds good. So let's come back to our chapter 6, equilibrium. Chemical reaction equilibrium for ideal gas. So in chapter 6, so far we went over the trouble of say, hey, what is reaction mixture? What is like ideal gas mixture? How do we define equilibrium constant for ideal gas reactions? And then at the end of our last lecture, we went over discussion of the temperature dependence of the equilibrium constant, right? So basically we went over the derivation to get to this expression here, right? So d ln Kp over dt equals to delta H naught over RT square, right? Or if you plot ln Kp naught versus 1 over T, you get a linear relationship with reaction enthalpy. So using this equation here, let's do an example question. We'll see this ammonia formation reaction very often because, well, it's one of the most important reactions in chemistry to form ammonia, right? It's one of those industrially relevant equations in chemical engineering. Now in here, if we read the question, we see that in here, can you use this figure, which is the figure 6.6b, to estimate how does the reaction enthalpy, what is the reaction enthalpy for the ammonia formation reaction for the temperature range from like 300 Kelvin to 500 Kelvin. All right, so in this question, let's just say, write out, what do we know? What do we know? So in our previous lecture, right, we went over the derivation of the Van 't Hoff equation, which is the plot of d ln K naught over 1 over T, gives you negative delta H naught over R. Right, so what does that mean? So on the left-hand side, this is the slope of the curve ln K naught versus 1 over T. Right, and we have the graph here. So in order to answer this question, we simply need to find 2 points on the graph and then solve for the slope and use the slope we solved to derive what the delta H naught is. And note that the question said it's asking us to estimate delta H naught in range of 300 to 500 Kelvin. The point of saying estimate is because delta H of the reaction is technically speaking dependent on temperature. But when the range of temperature change is small, we can assume it's independent and estimate it within that range. Right, so in this question, for example, we can say, all right, 300 to 500, so it's safe to pick somewhere to say, hey, this one is like at my ln Kp in my point 1, my ln Kp equals to 0, and we see my T minus 1 is about 0.0022 per Kelvin, right? And we can pick another point, let's say maybe here, when my ln Kp, when my T minus 1 is about 0.0040, and my ln Kp naught is about 20. You can pick any 2 points on this like straight line. It's a linear relationship, so it doesn't matter which 2 points you're picking. And you can solve for the slope. And that's delta y over delta x. So that's 20 minus 0, and then 0.0040 minus 0.0022. You get the slope to be about 1.11 times 10 to the 4th Kelvin. All right, and note like y slope has a unit of Kelvin. Your line k naught p doesn't have any unit. Your x-axis is 1 over t, so the slope must have the unit of temperature. And then later on, we're just plugging the relationship that we find out is like slope equals to times negative r gives you delta H naught. Right, so we can plug in the number to solve for delta H naught of the reaction is negative 92.4 kilojoule per mole. All right, so this question looks very straightforward, but I do want to pause here before we move on to go dig a little bit deeper into this reaction of ammonia formation to get more like conceptual understanding in like how does equilibrium, what does thermodynamics are actually doing in a specific reaction equilibrium like this one. All right, so the question I'm trying to ask here is, let me make some new space. Again, considering the reaction of my N2 gas plus 3 H2 gas goes to 2 NH3 gas. Can you plot, can you predict how does my R ln Kp naught, delta G naught of the reaction, delta H naught of the reaction, and delta S naught of the reaction change with respect to temperature? All right, so I'll give you a few more information. So we can assume Cp naught is constant. All right, so there are 4 different things, including our equilibrium constant, delta G naught, delta H naught, and delta S naught. So this plot is available in the textbook, and we'll do it together here. So what are we looking for? So effectively, what are we looking for is a plot. On the y-axis is some form of energy, and on the x-axis is my time. All right. So what are the things? Where do we begin? Like, let's think about what do we know about how does this reaction change with respect to temperature. So first thing first, we have an idea about, let's say, delta S naught, right? What do we know about the change of entropy of a reaction? First thing we know is when temperature approaches 0, my delta S naught also approaches 0, right? So that means my delta S plot must start at my 0 point when temperature is approaching 0. So this we went over when we talk about the third law of thermodynamics. What else do we know? What do we expect our delta S of the reaction be? Right, so this is an ideal gas reaction. We start from 4 molecules of reactant gas molecules. We end up with 2 molecules of reactant gas molecules. So we expect the delta S of the reaction to be negative. Right, so naturally, we can then draw our plot. Right, we start from 0, and it's more like a negative plot. It's not quantitative. It's just showing like, hey, my delta S is a negative number starting from 0 with respect to temperature. Sorry, this one should be temperature. All right. What about delta H? So the dependence of my reaction enthalpy on temperature, this we discussed in our chapter 5.5. Right, so we end up saying delta H equals to the integral of my delta Cp naught dt. Right, so in this question, we're giving you that my delta Cp naught is a constant, so delta H is pretty much just a linear function as my temperature. All right. And what else do we know about the reaction? So in the previous derivation, we find out this reaction has a negative delta H or a ectothermic reaction. So that means we start somewhere, and it's like a linear reaction, linear curve coming down. They have different dimensionality. Again, the plot itself is not quantitative. I'm just giving a qualitative expression in like what exactly are the trend of these state functions with respect to temperature. Okay, so now we have delta H and delta S. We can use our thermodynamics to derive how does my delta G change with respect to temperature. Right, so what is our delta G? So we know that delta G naught equals to delta H naught minus T delta S. So when temperature approaches 0, my delta G naught equals to delta H naught. That's something just like by looking at the equation, we know it is true, right? So my delta G must have the same starting point as my delta H. All right, what else do we know? We have delta H being a negative number. That's where our starting point is. We have delta S also being a negative number, but in delta G here, that's negative T delta S. So when temperature increases, my delta G also increases alongside with my delta S being more negative. So my delta G plot would look like this. All right. And what about my ln K? What about my equilibrium constant? Now for equilibrium constant, we have a few things that we know. The first thing we know is my delta G naught equals to negative RT ln Kp. Right, so if we're plotting my R ln Kp, we know that if my delta G increase with respect to temperature, my ln Kp must decrease with respect to temperature. All right, that's the first piece of information. That's because of the negative sign here. In addition, what else do we know? What about this point? So at that point where delta G naught equals to 0, my ln Kp must also equal to 0. Right, because my R is a constant, my temperature is a non-zero number, so when my delta G equals to 0, my ln Kp must equal to 0, and hence we have the plot of my ln Kp to be something like this. It's not a linear plot. This one is, again, not quantitative. I'm just like randomly saying. All right, and that's my RT, R ln Kp. And what kind of information can we get by reading this plot? Right, so for example, at this point, we know that my ln Kp equals to 0. So that means my Kp naught, which equals to our product of your partial pressure at equilibrium over P naught to the stoichiometric coefficient, right? So that product must equal to 1. And using this relationship, you can predict, like, what if I have lower temperature? What if I have higher temperature? How does my equilibrium composition change with respect to temperature? All right, and in addition, analyzing this plot you can also validate our understanding. So like what we said, we find out that R ln Kp must decrease when temperature increases, just based on the sign of my delta G naught. Right, so we get this plot by analyzing delta G naught. What if we're using our Van 't Hoff equation? So in our Van 't Hoff equation, what do we have? So in our Van 't Hoff equation, we have our d ln Kp naught over dt equals to delta H naught over RT squared. Right, so using the Van 't Hoff equation, if my delta H naught is negative, so what does that mean? A negative delta H naught tells me the ln Kp naught would decrease when temperature increases for this exothermic reaction using the Van 't Hoff equation. All right, so this one is like a quick demonstration in like how much information you already know for a chemically important and for a like industrially relevant reaction. Now we can extend this conclusion into like a new reaction, right? What if we have an endothermic reaction? What kind of plot will you get? Can you reproduce that plot? Right, so whatever we discussed on this diagram, there's nothing new here. We're using all the things that we discussed before. But then again, thermodynamics talks about relationship between your state function, knowing how the state function change with respect to temperature. And that derives eventually to knowing how the equilibrium constant change with respect to temperature. And that later on related to equilibrium composition, right? How does the equilibrium composition change with respect to temperature? All right. Okay. So then we're ready to move on to further use our Van 't Hoff equation for ideal gas reactions. So in this part, I want to quickly say, like, what is Van 't Hoff equation and what are we using it for? So in the Van 't Hoff equation, we have d ln Kp equals to delta H over RT squared dt. Right, so this delta H here, it's something we can get from thermodynamic table, which is delta H naught at 298 Kelvin. Right, so this is something we can get from the appendix table. If we take the integration on both ends, what are we getting? So on the left-hand side, we got ln Kp naught at T2 minus ln Kp naught at T1. And on the right-hand side, we have the integration of my delta H naught over RT squared dt. And then there are two different things we can do to solve this expression. First thing is assuming our delta H naught is not changing with respect to temperature when temperature change is small. So scenario 1, my delta T is small. So that means my delta T is smaller than, say, for example, 300 Kelvin. We can assume delta H naught is constant. Then in the scenario 1, we simplify this relationship to say ln Kp as T2, well, let me put the logarithm out, divided by Kp naught at T1. That's the left-hand side. And the right-hand side, we can take delta H naught, assuming it's not changing with respect to temperature when delta T is small. And that's roughly equal to delta H naught over R and 1 over T1 minus 1 over T2. And note this is true when we say delta T is small. Right. Alternatively, if we have larger delta T, we want to go back and use our temperature dependence of delta H naught. So again, what we have found out is delta H naught is a function of T1 to T2, delta Cp naught dt. And the Cp naught is basically something experimentally we can measure that equals to like a polynomial, so a plus bt plus ct squared plus dt third, depending on how accurate you want it to be. So this basically tells you this is a property we can measure experimentally with respect to temperature, right? We can get a random curve, and we use a polynomial to get a mathematical expression of that curve. Now, taking these two together, so when temperature change, so the scenario 2, when delta T is big, let's say 5,000 Kelvin, right? So you want to use these two together to solve for the delta H naught, to solve for delta H of the reaction as a function of temperature. Et cetera, right? And you can then plug in this delta TH into our delta H naught as a function of T over T squared dt, and solve for how your equilibrium constant change. All right, so this part is like a little amendment in like how exactly do we use the Van 't Hoff's equation. So what is the point of the Van 't Hoff equation? The Van 't Hoff equation gives us the equilibrium constant dependence on temperature, right? So we can use our tabulated data to solve for the equilibrium constant at, say, 298 Kelvin, which is appendix data temperature. And then if we're talking about a reaction at a different temperature, not at 298 Kelvin, we want to use the Van 't Hoff's equation to adjust for that equilibrium constant change at different temperature. And when we're talking about the temperature change, there are two different scenarios. One is when my delta T is small. That means you can just assume my delta H is not changing. And two, when my delta T is big. So we'll tell you what is the function of the heat capacity, the delta Cp naught. All right. So this part basically gives you a setup, right? We define our equilibrium constant. We went over like how exactly is my equilibrium constant change with respect to temperature? What's the relationship between the equilibrium constant and my thermodynamic state functions like delta G of the reaction? So now we're ready to move on to our lecture 19. So if you have your handout, we will do our problem together. So in this part, well, I think today I have time to go over my 6.4. So the structure is the following. We'll first talk about what is the general approach to calculate ideal gas, to do like ideal gas equilibrium calculations. Or basically, I'll give you a general scheme. And these are the steps we take in order to solve the problem, right? And then we will go into like one detail to say like use our ammonia formation as an example to demonstrate like what exactly am I mean when I have like the extent of reaction, right? And then we'll do one comprehensive problem together using that 6 steps to solve for a numeric answer. So let's get started in the general scheme in how to set up ideal gas equilibrium calculations. First thing first, before we start, always write down what are the things we know, right? We know that delta G naught equals to negative RT ln Kp. That's how our Kp is being defined. And then we have our Kp's definition. That's like a product, series of products of your partial pressure at equilibrium over P naught to the power of its stoichiometric coefficient. Now, this is very important to know that equilibrium constant is defined based on the partial pressure of each species at equilibrium. And in addition, in here, what is my delta G naught? My delta G naught at certain temperature is something you can calculate from tabulated data, right? So that's a stoichiometric coefficient, the delta G naught of formation at certain temperature for species I. That's something you can calculate from the thermodynamic table. Right, so let's look at the setup of our calculation. For any ideal gas reactions, we follow the 6 steps to answer the question, what is the composition of these ideal gases at equilibrium? Right, so what are these things? So let's say the first step is to calculate my delta G, or the Gibbs free energy of reaction from tabulated data at 298 Kelvin. And then we can calculate my delta G using delta G naught equals negative RT ln Kp to calculate the Kp naught at 298 Kelvin. Note that you might need to take one more step to calculate the reaction equilibrium at a different temperature if we're asking you to find the equilibrium constant at something not at 298 Kelvin. So this means you want to use our Van 't Hoff's equation for Kp naught at some other temperature. All right. Now, in our part 2, effectively, we're just solving our equilibrium constant at certain temperature. And now, how do we use that equilibrium constant to solve for the composition or the number of mole of your reactant and product at equilibrium? So this part is more like Gen Chem, but we just want to standardize it using the thermodynamic language or the pChem language. So express equilibrium mole numbers, what does that mean? So in here, we write the number of mole of your substance I at equilibrium as a function equal to the number of mole of your substance I at initial condition. So this 0 represents initial, right? At the initial without the reaction taking place. And plus the mu I, the C of the reaction, right? So here, this one is our stoichiometric coefficient, and C is our extent of reaction. Now, with the expression available, like this one is basic equilibrium or the final state, initial state, the delta N, the change of your number of mole of that species. And then we can express the equilibrium partial pressure, Pi, right? We know that equilibrium partial pressure, Pi, equals to chi I over P times P. Now we have an expression on the right-hand side, right? So that's our equilibrium constant using partial pressure. On the left-hand side, we have something we solved using the tabulated data and the Van 't Hoff equation, which is equilibrium constant. We're just solving that equation for the extent of reaction and then calculate the number of mole of different species using the solved extent of reaction. So before we do a comprehensive problem together, let's just go in here a little bit more into this part, like 3 and 4, to make sure we're on the same page here, because it's been a while since we talked about reaction equilibrium. Right, so again, we're using our ammonia formation reaction as an example. Let's say we have our initial number of mole of my N2H2 and NH3. Right, so it's randomly putting like 1.0, 2.0, and 0.5. So the change of number of mole of each species, it's effectively the stoichiometric coefficient of each species times the extent of reaction. So this one is negative C for N2. negative 3C for H2 and 2 for my product NH3. Right, at equilibrium, then this becomes 1.0 minus C, 2.0 minus 3C, and 0.50 plus 2C. And naturally, we can calculate the total number of mole by adding these three terms together. Right, so at equilibrium, we know the total number of mole equals to the sum of my Ni equilibrium. So that adds up to be 3.5 minus 2C. All right. And from here, again, we have expressed our total number of mole. We have the number of mole of each species. We're ready to say, hey, what is our partial pressure at equilibrium? And now we have two different scenarios again. So scenario number one, let's say we have fixed total pressure, which is P. Right, so when my total pressure is fixed, we know that the partial pressure of each species equals to chi I times P, or the mole fraction times the total pressure P. Or this equals to number of mole of each species at equilibrium divided by the total number of mole of each species at equilibrium times the total pressure P. Scenario number two, if we have fixed total volume, right, so the pressure may be changing, but my total volume is fixed. And what else do we know? We have ideal gas mixture, so PV equals to nRT. Now my PI for each species must equals to Ni times RT over V. All right, so depending on the scenario, if the pressure is fixed, then your partial pressure depends on the composition of each species. But if volume is fixed, then the partial pressure only depends on the number of moles at that equilibrium. So it depends on the scenario, and use these two wisely. All right. And later on, we'll use our reaction quotient. So I just want to quickly define reaction quotient here, and then we'll use it later on. So for reaction quotient, in this case, we're defining our reaction quotient as like the product of all the partial pressure to its stoichiometric coefficient timed together. So equilibrium constant is something is talking about the partial pressure at equilibrium. But reaction quotient is like some random point. It may not at equilibrium. But comparison of the size of your reaction quotient versus equilibrium constant can tell us what's the direction of the reaction movement. So if the reaction quotient is smaller than equilibrium constant, then we say we have our forward reaction. And vice versa. So we'll discuss this later on in more detail. So again, this part is pure review, right? It's more like Gen Chem, just standardized with our physical chemistry language and vocabulary. And now let's ready to do the problem together. So here's the problem. Suppose that a system initially containing 0.3 mole of N2O4 gas that may decompose into 2 nitrogen dioxide. And we tell you the equilibrium is attended at 25 degrees Celsius and 2.00 atm. Can you find the equilibrium composition? Right, so we're following our 6th step to get a numeric answer in what's the number of mole of N2O4 and what's the number of mole of NO2 at equilibrium, which is reached at 25 degrees Celsius and 2 atm. So if you have your handout with you, let's just do this problem together, following the 6 steps we've discussed. First thing first. Right, the first step is to solve for delta G of the reaction. So this one, we can solve it using our thermodynamic table. So if you have your appendix table, perfect, you can use it. If not, I'm just going to tell you the answer here. So that's 2 times 51.31 minus 97.89 kilojoule per mole equals to 4.73 kilojoule per mole. So quick question here. What's the delta G of formation for my NO2? Which one? Which one of them is my delta G of formation of NO2? This one, right? So that's in front of, that's the stoichiometric coefficient in front of my product, which has a 2 in front. So basically, if you know that, you know where to find that tabulated data. Second question. Now we're ready to use my delta G to solve for my equilibrium constant. So delta G naught at 298 Kelvin equals negative RT ln Kp. And we're talking about the Kp naught at 298 Kelvin. So since it's always at 298 Kelvin, we don't have to use a Van 't Hoff equation in this scenario, right? So we can just plug in the numbers. We know that delta G naught equals to 4.73 kilojoule per mole equals to my 8.314 times 10 to the negative 3 kilojoule per mole per Kelvin times 298 Kelvin and ln Kp naught. So plug in numbers to your calculator. We get our Kp naught equals to 0.148. And by the way, you do need a calculator for this final exam if you don't already have one. What's the third step? So reading our third step, it says we want to express equilibrium more numbers, right? So we have our N of my species I at equilibrium equals Ni initial plus stoichiometric coefficient times the extent of reaction. I'm not very good at writing that C symbol, but you'll do better than me. So we can write that number of mole of my 2 chemical species involved. Right, so we can write the number of mole of N2O4 at equilibrium equals to the number of mole of N2O4 at initial plus the stoichiometric coefficient, which is -1 times the equilibrium, the reaction extension. And this one is the same for NO2 equilibrium, NO2 initial plus 2 times the extent of reaction. And what's our initial number of mole? We can read the question, right? So initial number of mole of N2O4 is 0.3. And for our NO2, that's 0.5. All right, so we end up expressing the number of mole of my reactant and product in as a function of the extent of reaction C. And we can write that out to 0.3 minus C more or 0.5 plus 2C. All right. The next step is to express our equilibrium partial pressure. What is our PI? So we have PI equals to pi I times total pressure P. And the reason we use this equation is our pressure is specified at 2 atm. Right, so in here we have P equals to 2 atm and chi I equals the number of mole of species at equilibrium over N total at equilibrium. I can also solve for n total of equilibrium. And that equals to the sum here. So that's 0.8 plus C. Right, so naturally, we can write the partial pressure of NO2 at equilibrium to be our partial pressure here. So NO2, that's 0.5 plus 2C divided by 0.8 plus C times total P. Partial pressure of N2O4 at equilibrium is here, 0.3 minus C over 0.8 plus C times the total pressure P. All right. So what's our next step? We have our partial pressure. We know what our equilibrium constant is by using the tabulated data. We're ready to set up a calculation using the definition of our equilibrium constant. So we know that our equilibrium constant Kp naught is defined as our product of partial pressure at equilibrium over the standard pressure to its stoichiometric coefficient. Right, so when we set up this calculation, we have 0.148 equals to the product. So here, my partial pressure is, well, 0.5 plus 2C divided by 0.8 plus C. Note we need to use our P over P naught here. That's our NO2. So we have the stoichiometric coefficient of NO2, which is 2. And times, for N2O4, we have 0.3 minus C divided by 0.8 plus C to negative 1 times the P over P naught to negative 1. Right. And in here, my P equals to 2 atm, P naught equals to 1 bar. So you want to take care of that unit conversion when we're doing this step. So keep in mind we have to do the unit conversion inside. All right, so this basically gives us a way. Now on the left-hand side, we have a number. On the right-hand side, we only have one unknown, which is the extent of reaction. So just plug in your calculator and solve this quadratic equation. And if we solve that quadratic equation, we find out we have two different roots for this equation. So my C can be negative 0.324 more or negative 0.176 more. So both of them are negative, suggesting it's backward reaction. But now we have one more step to think about. Now, if it's a backward reaction, how many number of more of my NO2 is available in my initial mixture? I only have 0.5 more, and there's a stoichiometric coefficient of 2 in front of my NO2. So this one cannot be true. We don't have enough number of more of reactant for my C equals to negative 0.30, anything larger than negative 0.25. All right. And at the end, we have our calculated C equals to negative 0.176 more. And we're ready to plug in that into here to solve for the number of more of my N2O4 and then NO2. That's our step number 6. All right. So if we think about this question, we started simple. We started by looking at the initial number of more of my reactant and product. We use our tabulated data to finally be able to solve for, hey, at this temperature, what is the composition of my reactant and product when we reached reaction equilibrium? So it's very powerful. It's like something like super powerful. Without doing any measurement, you know what's the composition of your reactant and product at equilibrium. So this is the example of getting the numeric answer. So in our next lecture, we'll spend more time looking at examples of, for example, we have equilibrium composition, but now instead of getting numeric answer, let's say, can you express the number of mole or the mole fraction of different species using the equilibrium constant provided. And then in our next lecture, we also will spend lots of time talking about shifts in ideal gas reaction equilibria. So this part is to give you an intuitive understanding in like, how does the equilibrium move? Like, for example, if I change my temperature, I change my pressure, change my volume, I add inert gas into my mixture, or I add reactant and product, how does it change, right? So that's the goal of our next Wednesday's lecture. And again, I won't be able to discuss the phase rule with you, but hopefully we will be able to finish chapter 6 in our Wednesday lecture. So I'll see you in 2 days. And